Hi, thank you so much for attending today's webinar. Just to go through a few housekeeping items before I turn it over to today's speakers. Everyone is on mute, so if you have questions throughout the webinar, please submit those via the question box, and we will address questions at the end of the webinar. We're leaving about 20 minutes for those. So definitely submit your questions, and if we don't get to them, we will follow up with you via email after the webinar. Just a few other little things to keep in mind. We are recording today's webinar, so if for any reason you need to jump off the call, we will have a recording of the webinar up on our website along with presentation slides in about 10 days. So on that note, I'm going to turn it over to Na Nguyen, who is with the DOE, to introduce today's speakers.
Thank you, Ali.
Na?
Hi. Thank you, Ali. Hello, my name is Na Nguyen, and on behalf of the Fuel Cell Technologies Office, I would like to welcome you to today's webinar. I would like to say a few words before we proceed. This webinar is designed to be an informational webinar for the public on hydrogen fueling protocols. Moderating today's webinar will be Mr. Rob Burgess of the National Renewable Energy Laboratory. Rob Burgess has been an expert in this field. We are also pleased to have our two speakers today, Jesse Snyder from BMW North America and Steve Matheson from Honda North America. I now will turn it over to Rob. So thank you and welcome everyone.
Thank you, Na, and we'd also like to thank the Society of Automotive Engineers for providing some of the content of this webinar. Just to set the stage here, what I'd like to say is that there is a 2015 commercialization release that has been announced for hydrogen and fuel cell vehicles. So there has been a lot of activity relative to getting the infrastructure in place. So this is certainly one of those activities. And as you know, hydrogen, light gas, is stored on board vehicles now as a gaseous fuel, very similar to a CNG. However, CNG vehicles are also gaseous onboard storage. However, for hydrogen, with the higher pressures, 70 MPa, and some of the thermal characteristics, there are some additional technical issues relative to trying to put these infrastructure dispensing stations in place. So the Society of Automotive Engineers will hear the SAE J2601 subtask group input that Jesse will be presenting. I'd like to go through the quick bio on both the speakers, and then we'll get our webinar started. So Jesse Snyder, our first speaker, is the manager of fuel cell electric vehicle development and standards at BMW USA. He recently relocated from the Munich office of BMW, where he was the project manager in charge of the 70 MPa storage, as well as internal and external standardization of fuel cell vehicles. Prior to this, Jesse worked at automakers in both the US and Germany, with testing and systems integration responsibilities ranging from conventional production vehicles to electric and fuel cell vehicles. External to BMW, Jesse has been leading document development of hydrogen fueling protocols, the SAE J2601, SAE J2799. He also led first efforts in establishing emergency response for fuel cell vehicles, in developing hydrogen dispenser test device, and in creating a hydrogen quality specification at the California Fuel Cell Partnership. Jesse has a BS degree in International Mechanical Engineering from the University of Rhode Island, as well as a diploma in electronics. Our second speaker, Steve Matheson, is a senior engineer in the Energy and Environmental Research Group at Honda R&D Americas Incorporated. He has a BS degree in mechanical engineering from the University of Idaho and has an MS degree in engineering mechanics from Virginia Polytechnic Institute. Steve's research focus has recently been in the area of hydrogen refueling, where he has developed a novel approach for controlling the fueling process called the MC method. Steve is also actively involved in the work being conducted to bring SAE J2601 to a full standard. So with that, what we'll do is, and you should see on your screen the cover slide, we'll hand it now over to Jesse Snyder of BMW to begin the webinar presentation.
Okay, Thank you, Rob, for the introduction. I want to thank the DOE for the invitation, and American Honda, where we're sitting right now, for putting together a meeting space for us to have this presentation. This is the portion that I'm going to present. I'm sorry, I didn't move the slides forward. The portion that I'm going to present is the the J2601. That's the currently a guideline for light-duty hydrogen fuel cell hydrogen fueling protocol, and that is a team of many people from automakers and fuel providers that have worked for the same purpose of bringing hydrogen fueling to commercialization. And we're not going to show you much about the 2799, which is the nozzle and the communications, but we'll reference to it. This picture, I just wanted to acknowledge also that it's really an international effort. It's not just the United States, so to speak. These are just a few examples of stations that are using SAE J2601 in their day-to-day fueling. There's a station in Hamburg, Germany, that's shown on the left, and that does vehicles, light-duty vehicles and buses. On the right-hand side, there's Hi-Suit and JHSC that have hydrogen fueling stations in Japan. And right here in California, where I'm sitting right now, actually, there's a station, for instance, in Emeryville that's doing light-duty vehicles and buses that has J2601 as the reference point for the fueling protocols. And I would like to acknowledge that we could not have gotten here just with consensus with the industry. We also have a lot of government and partnerships involved. So underneath this, there are actually partnerships, for instance, that have supported the effort. The Clean Energy Partnership in Berlin, Hydrogen H2 Mobility in Europe, in the United States, the DOE, the California Fuel Cell Partnership, ARV, and the California Energy Commission. And in Asia, or in Japan in this case, Hi-Suit, the Demonstration Project, FCCJ, JARI, and NITO, all of which have been a great supporter. And we really appreciate their efforts to help us make this document. Moving forward to the outline, I'm just going to show the current status of the guideline and give you a little bit of a peek of what's coming in the next version, or in the standard version very soon. We're going to talk through the standardization timeline, very short overview of where we were and where we're going. Talking about the fueling background, why hydrogen fueling is so important to the fuel cell vehicle commercialization. We also have the content of 2601. It's a tables-based approach. We're going to get into a little bit of the theory and the modeling, and talk to you a little bit about some of the validation testing that was underway to get us to the confidence to publish. And I'll also mention that SAE is not alone in this. We've also worked in the past with other organizations like the Canadian Standards Association with regards to the station testing, where we have an option to use that. And as I mentioned, this is the first time ever we're going to really show publicly what the SAE community or the SAE team, the interface team, is really thinking for the standard version. And I think that we're planning, I'd like to state this up front, we're showing us the state or the status of the document. And there is more to be had, so to speak. There's more that we're improving what's in the field. And we're planning a follow-up of this webinar probably within the next 6 months. And we'll, I'm sure, make sure that you have that information at a later point. So without further ado, let me just get into maybe just an overview of where we were, where we've been. Modern hydrogen fueling, I mean, hydrogen fueling has been around for a number of years in other industries. It's the largest industrial gas in the world. But in vehicle fueling, it really began in the late 90s. I'd like to mention there are some pioneers like Frank Lynch, a very good colleague who'd been doing hydrogen fueling since the 1970s, who actually started to think about concepts like communication refueling. He and his colleague also had worked on pre-cooling, all these things they put into the public domain and published. We all did a gratitude for that. For many years, starting in around 1999, the partnership in California had worked on hydrogen fueling and with communications. at that time, wired communication to the so-called I/O guideline that was never published externally but became the de facto world standard immediately. When I remember going to a conference in Italy and seeing a station that had the California Fuel Cell Partnership Protocol. So I think we really understood at that time that the way is to go through a standardization process to make sure everyone's on board. Around 2007, we realized that we wouldn't get to the ZEV range, this longer range of 300 miles, without having higher pressure on board. And the goal is to get to 70 megapascal. In 2007, the automakers got together, 8 automakers got together, along with 2 hydrogen providers, and published a document in the public domain on hydrogen fueling using a ramp rate similar to what we have today, and referencing IRDA communications, etc. And in a document I'll explain in a second. And this document was published in the United States and was also published simultaneously or a year later in Germany to give guidance to stations. We now call it Rev A, and it's actually the precursor to 2601. Simultaneously to that, in 2007, the first guideline on 70 megapascal coupling, as in the nozzle receptacle geometry, was published along with the infrared data in 2007, and that gave enough information and confidence to publish also with fueling data in 2010 the first hydrogen fueling guideline. That's really going to be the focus of our discussion. I will spend more time on the content of that guideline, but one thing I'd like to make clear is that we're really targeting 2013, this year, to take lessons learned from the field and standardize the hydrogen fueling protocol. So just getting into some of the background, it's quite simply one of the major factors for success in the hydrogen economy or hydrogen fuel cell vehicles. Customer expectations are basically the same as today. They want a safe fueling in a very short amount of time with a very high density, meaning they want to have range, the same as gasoline. And we all know what the present technology is in electric vehicles in terms of charging. So in terms of hydrogen, that offers a leapfrog in terms of ZEV technology to give the same as today's fueling rates. So the goal of hydrogen fueling with 2601 is really to achieve this high state of range without exceeding the storage and safety limits, and I'll get into that in the next slide. One thing I'd like to mention and acknowledge that we've always had in mind commercialization goals. The U.S. Department of Energy has probably published the most comprehensive list thereof worldwide in regards to what is needed. And one of the targets regarding hydrogen fueling is met. The 2017 targets is met. This 3.3 minutes with 5 kilograms hydrogen storage with J2601. So when I referred to before, what do I mean by electric charging versus fuel cell? I really don't want to make this as a competition, because I think that electric vehicles have definitely a place in the commercialization of ZEV vehicles. But just the fact, we need to just state the facts that there are 2 standards out there, 1772 and 2601, and just comparing the two in terms of storage versus refueling time. A conventional electric vehicle is about 30 kilowatt hours. The same fuel cell vehicle is about 100 kilowatt hours, just because you get there's a lot more energy density in the hydrogen than what you can get out of the battery. And that's not usable necessarily. I think, let me rephrase it again. The hydrogen, of course, is all usable all the way to the end of the tank. The electric vehicle, the battery is not necessarily usable to the entire rating. But to give a fair assessment, this is the published ratings. So really, for between 100 and 200 kilowatt hours is what is possible in light-duty vehicles, what 2601 is offering. And this is a reference to a C&E segment. And the vehicle charging really gives you the 3 to 50. The 3-minute fueling is with a Type A dispenser, and the 50-minute fueling would be with a Type B dispenser. I'll show you that later. So that will give you about 300 miles, 500 kilometers, where today's technology gets you about a fourth of that in terms of range in electric vehicles. So when I was referring to before in terms of storage limits, we have this magic number of 85C. We also have a maximum pressure of 25% above the normal or nominal working pressure, which is in this for 70 megapascal, 87.5. We have targets of 3 minutes fueling rate within a density of 90 to 100%. This is not the same as as a liquid fuel, but it's very close. Vehicle-to-station interface strategies. We have communication and non-communication, and we have controlling factors also in order to offset this heat of compression inside the tank. We actually pre-cool the hydrogen. Regardless of method, we have to do that. Hydrogen delivery rate per station, is really per mass or pressure and time. We actually do what's called an average pressure ramp rate, which means any vehicle pulling up will get the same, under the same category, will get the same fueling time. And we also have a field determination. The challenge of compressed hydrogen fueling is this heat of compression is really the key, and keeping the 85C is another factor. Also because, for instance, the Type 3 tank reacts quite differently. I should say the heat generation is lower, for instance, than a Type 4 tank, but we need to be technology neutral. So regardless of a Type 3 or Type 4 tank, we need to make sure we cover that. So we have, for non-communications fueling, we really don't know what the storage tank temperature is or the tank properties, but we do know through the dispenser side what the pressure is and, of course, the ambient temperature. So we would like to, 2601 would like to allow the possibility on the vehicle side to have communications and non-communications. The station side must have communications to offer that option. Okay, so the station must estimate temperature change that occurs during fueling. And there's also factors in that temperature change, including the starting temperature, the capacity, type of number of tanks, etc. Okay, so what I'd like to do is really start in discussion of J2601. We already mentioned that it's really meant just for light-duty vehicles. There are other documents that are working on forklifts and heavy-duty buses that are not yet published but in process. This is really just light-duty vehicles, just I say. It provides guidance for hydrogen within reasonable fueling limits, as already mentioned, and it gives a set of tables that has pressure targets in it to achieve this 90 to 100% reasonable state of charge under all temperature conditions from -40 to +50. So fueling protocol was actually created by 7 automakers setting their actual tanks and testing them under extreme conditions. Like I said, I just leave this as a placeholder that the standard is coming in 2013. So just to explain to you that we are, because of this great unknown, so to speak, of what, especially in non-communications fueling, we have these lookup tables. There are, however, these input parameters, like the vehicle side, the inlet, the initial gas temperature, initial gas pressure, the station parameters, the ambient temperature, and the delivery gas temperature. And with these tables, we get the output, which is the ending pressure, and the refueling gas flow rate or ramp rate that will get us to our fueling assigned, so to speak, for that vehicle pulling up. I mentioned before, to offset the heat of compression, we need to pre-cool the gas, and the speed of the fueling is directly related to the pre-cooling temperature. The lower it is, the faster the fueling. So this Type A station really is the premium, or this temperature of -40 is the one that will get us to the fastest fueling time. So we have for 70 megapascal only types A and B available, -40 and -20. Those are types A and B. And we additionally allow for 2 more types for 35 megapascal because the heat of compression is less in that pressure range. So type C station has 0 degrees pre-cooling, so to speak, and for the type D, it's basically ambient temperature. It has no pre-cooling, and that's a much slower fill. Only those last two, as I mentioned before, only for 35 megapascal. What I thought I'd do is take you through the inner workings of the fueling procedure. We mentioned before that you have really two options of types of fueling, so to speak, with communications or non-communications. If you don't have a signal, let's just say, or something is not working for whatever reason with communications, you simply just default to the non-communications if it's not working or if there's a break in the signal, for instance. So if there's no communications, if no IRDA signal reach, the lookup tables first starts off with the fueling station type. As I mentioned before, the dispenser type is this A through D. Based on the ambient temperature, you also have some initial measurements from the tank pressure. And there's a way to determine the size of the storage pulling up to the vehicle. We call it a pressure pulse to determine what the capacity of the storage pulling up. Then we have these lookup tables. Each one of them is assigned to this pre-cooling limit that assigns an average pressure ramp rate and a fueling target. And as long as the pressure is less than the target and the delta P of the station to the vehicle, you can fuel. And if there are any concerns with pressure going on to the station, I can decide to shut down. Just like that, on the communications side, there's a set of tables for every dispenser type. But this time, we actually have the advantage to have vehicle data. With the vehicle data, even if it's transferred, if there's any issues with the validity of that data, it will default to non-communications. It's very simple. If the data passes, then you have these lookup tables that give you the same average pressure ramp rate in the left, but give you slightly higher density. And the advantage that it also offers communications is anytime the vehicle thinks it needs to shut down, it can. And it also gives you much higher as confidence, I should say, in state of charge. Okay, so fueling fundamentals. We thought we'd just walk you through a little bit of the theory. SAE 2579, aligned with the global technical regulation, gives the safety limits in pressure and temperature and cycles, et cetera, for hydrogen storage. It's already done. It's already published. You can buy it today. We, in the fueling world, align with that, and we say that we will not go above 85C, and we won't go above this 25% above the nominal working pressure, in this case 87.5. What we're showing here, because pressure and temperature equal to, you can have the density with the properties of hydrogen. This line, we call it actually the line of constant density, where regardless of the pressure and temperature, the reference temperature, once it settles down to the 15C, which is the line needs to move a little bit, but it will give you exactly 70 megapascal. This line of constant density, what the objective is to keep this 90% band underneath and not overfill. As if we don't want to get, or we don't want to make a higher than 100% SOC if we can avoid it. If it goes a little bit below 90%, like 88%, there's a few cases in the TIR that actually does that. We still allow it, but it's much lower than that is not allowed. So you have these limits of pressure and temperature, and you have these targets for performance. To understand how these things are developed in 2601, the assumptions that were developed for hydrogen fueling, we also have to understand if we have non-communications, we don't know what's going on with the tank, then we have to understand what are the cases of ambient temperatures and also the temperatures in the vehicle. So we actually have, you actually have these hot soak and cold soak conditions, which are taken into account in order to develop the tables. The hot soaks, extreme cases, that in real world, really we stop around 50, so to speak. There is, cold zones that stop around -40. Why don't I just get back in? What I want to do is, this is kind of a quick jump, but what I want to do before I explain a little bit of the detail of how the tables were generated, I wanted to just mention it's relatively simple, the lookup tables results, so to speak. For the dispenser, they have this lookup table, for instance, as I mentioned before, for an A70. And what I want to do is show you an example of the target pressure that the dispenser uses for control logic. So what happens is a vehicle pulls up. Let's just say it's completely almost on E, or let's just completely empty, but it's actually, let's just say it's at 2 megapascal, a low state of charge, and which is this up here. You see this initial tank pressure from the vehicle, and then, but he pulls up on a cold day where it's 0 degrees outside. The dispenser then decides, okay, we have a target at the end of fueling. Your dispenser should shut off here. Every dispenser has, from the CSA world, protection in regards to overpressure and things, and et cetera, et cetera. But these targets will get you within, this 125%, so to speak, of the nominal pressure. You understand? Sometimes you have to go above 70 megapascal. That it will, when it cools down, it'll settle down to 100%. So at 0C, the vehicle pulls up at 2 megapascal, and then this ramp rate of 28.2 megapascal per minute. So, effectively, just about, 3,000 psi per minute ramp rate. And literally, the dispenser has this lookup table programmed into the PLC, the programmable logical controller, and it's able to for whatever tank pressure that comes in, that it can also iterate between these pressures, and for whatever ambient temperature, from realistic temperatures from -40 to +50, it can determine when the dispenser should stop and the average pressure ramp rate to get us our targets. I thought I'd take a few minutes to walk through how that was derived, because I understand there's some folks on the technical side who would like to have a little more insight. So, non-communication case protocol development was developed. Well, it really was developed for 2 cases, but for both non-com and com. But the protocol is based on, as I mentioned before, the known parameter values and possible ranges of unknown parameter values. Some of these hot and cold soak, I didn't explain it all the way, really are to understand what are the worst case scenarios for temperature. For step, we've developed what we call a 3-step simulation process. The first step determines the hot case. In the fast fueling, of course, is desired, but we want to make sure that when this ramp rate that we have put into this table does not increase the temperature past 85. And the step 2 target pressure, the full fueling is desired, but we don't want to have a target above 100% SOC. And this third step is really to assess how well we're doing in terms of the results of SOC. So there's a range of real-world applications based on ambient conditions and tanks in that category. So step 1, this hot case, we have a hot soak, for instance, of, this is an example, by the way, hot soak of 20 degrees C, and this hot case vehicle where you have a Type 4 tank, which has the, as I mentioned before, the the properties of an insulator, which heats up faster than a Type 3 tank, which is sort of a heat sink. It's parked first in a hot environment and then fueled from empty. So you can imagine you're at a rest stop and you leave the vehicle parked in a hot day, and then you just pull up to a station without driving very far. In that case, you determine the average ramp rate, as in how fast can you go in this pressure ramp rate without over-temperaturing the tank. Step 2 is the other side of the equation, the cold soak. There are conditions, for instance, we call it in some ways we've called it in the past the Autobahn test, when you're driving under high loads. And when you defuel a tank at high loads, you tend to cool the tank. But anyways, if you have a cold, this is actually another condition where also we have a cold soak condition, 10 degrees below, for instance, the ambient conditions. It has to do with another type of tank, the other type of tank that's the unknown of pulling up, which is a Type 3 tank. The cold soak is followed by a rapid defueling, and then it pulls up to a station. And that station does not know that the temperature of the tank is colder than the ambient. So we have to take that into account, that we don't over-density the tank. So then the fuel's temperature is brought to the lowest temperature, sort of on this minus 40 C, and we get to 100%. And this cold case vehicle defines the pressure target, so we don't over-density. And then in step 3, we take this worst case, or we take this case and run it again and find out what is the worst case state of charge. So I'm working through this backwards because I've already shown you the results of the tables, but I wanted to show you the series of lookup tables that specify the fueling rate and target pressure as a function of ambient temperature. We've already gone through this. We said that the lookup tables give the 3 to 5 minutes or less in most conditions for this Type A dispenser, and it's actually related to the size of the tank as well. The fueling times, if you don't have any, this is something I should have mentioned before, but if you don't have any pre-cooling, it's kind of like that LensCrafters commercial. Expect to wait about an hour or so. It's really long. I mean, I think it's something that we're coming to the realization. There are some applications like in the future, something Honda's evaluating home fueling and things like that, which may be interested with non-pre-cooling, but it's not a commercial aspect. Anyways, getting back to these tables, non-communications are expected between 90 and 100%. The lower end of the density or of the range, so to speak, is on the non-communications, and with communications, you have a higher SOC possible. Okay, so I wanted to just show sort of an example of the, for instance, 2 type of dispensers with a certain category. So the J2601, the present document, has a storage capacity of 1 to 7 kilograms, and then 7 to 10. So that's how it's grouped. And in those categories, if you look here, under, let's just say, the 90th percentile of fuelings, typical of 3 minutes, you see it gets a little slower when we're talking about, Death Valley when it's very hot outside, which is acceptable to most. However, with regards to Type B, you get a slower fueling. It's difficult to average when you see these variants, but let's just say between 10 and 15 minutes is typical. Depending on the range of how much is in your tank. For instance, if your tank is a third fuel, you'll get a relatively quick fueling rate, less than 6 or 7 minutes. So non-com and com are compared. We get about 90% on the lower end of this. We had mentioned before we've done this running with step 3. And this is how we got these 90 to 98%. With communications, we've even seen this in the field, a very high confidence of the state of charge. 98 to 100%. So we think that's pretty good. So I wanted to mention, this is an older study that was done years ago. I should mention this was done at PowerTech. The purpose was to confirm the fueling meant to be used for SAE guidelines and later standards. So really, it's the guideline level, and determine the 35 and 70 megapascal fueling parameters for each OEM system. This was a really large study. I'd like just to acknowledge that at that time there was a lot of involvement with the oil companies and BP, from the hydrogen companies, from Air Liquide and Iwatani. I should say Shell was also involved for that, Sandia National Laboratory, and the U.S. Department of Energy was a very big supporter in that regard. Vehicle OEMs that were participated, there are 6 that are mentioned here, and there was one more that came a little later. So Daimler, Chrysler, Ford, GM, Nissan, Toyota. And the results were used to validate 2601 and 2799. So it was a very valuable study. There was at that time the organization was called Freedom Car. I think it's called now. Well, at that time the organization at DOE had put together a baseline document for the purpose of testing. They even went as far as the coming to a common instrumentation for the tanks. All the automakers involved in this study instrumented their tanks in that fashion. It was a very, very, very impressive coordination effort. PowerTech did a great job testing these extreme conditions and the basic understanding and validate tables. And this data was shared with the 2601 team. The interesting thing about this is we did studies even in the beginning trying to understand this is where what the best case pre-cooling conditions were, and also we understood at that time -40 seemed to be a magical number that gave us the very high confidence that we could get a fast fueling. And below -40 for 70 megapascal was deemed to be not customer acceptable also through this study. We also did validation of the nozzle, et cetera, and the selection of the nozzle also came from this, the selection of nozzle worldwide also came from this study. And at the right is shown the laboratory setup where they had the breakaway hose, nozzle, et cetera, and the tank inside. You know, the scope of the work examined over density, over temperature, and target SOC fueling, and also did some work regarding the tables. So it did validation of the modeling and also did validation of the tables. Just to show you, these are actual examples. We initially, on the left-hand side, did sort of a theoretical investigation of what is the optimal pre-cooling temperature per actual automaker systems with different types of tanks. So Type 3 and Type 4 tanks were investigated. We really did a fundamental understanding of hydrogen fueling. We didn't just start with these numbers. And the result of that is where we came up with the 3-minute fueling. I'm going to tell you which OEM because we were sworn to secrecy, but this is a result of an actual automaker system inside of a temperature chamber that actually it was a Type 4 tank, I can say that, that gave us a higher confidence of this fueling protocol. We also did, this is just showing you some data, target SOC, state of charge. We had, this is a larger than 6 kilogram tank that we were able to fuel within target of the tables. We also did, there's also an SOC test. There was other tests that did a very good overview of what we needed for the table validation. So where we are today is that we have a published document, and there's an option to use in order to test the fueling protocol. Let me step back. In order to test the fueling protocol, the industry has determined it's best to do so when you first validate a station with a device. This device is actually shown as an older one, but something that works for 35 megapascal. The California Fuel Cell Partnership had put it together, and their members had paid for it back then. I know CSA is working on a hydrogen dispenser testing apparatus. But in general, hydrogen dispensing testing apparatus is a mobile device with instrumentation and representative tanks to evaluate performance of the dispenser. The Clean Energy Partnership in Germany is currently underway building one. I know CSA America is underway building one. So one option is to use CSA 4.3, and I'm sure that as time goes on, we'll see the commercial application of this. I know that I think this solicitation here in California for the hydrogen stations actually references J2601, and using a test device like CSA 4.3 to validate that the protocol actually works. So that was 2601, and what I want to do is show you the next version, and just keep in mind, because the team is not consensus on it, we can only show you a very small cross-section of what we're working on in terms of the actual content. However, I'm going to show you something. This is the list of what we're doing. We're taking the 2799 portion, and we're rolling that into 2601 in terms of communication, because the 70 megapascal nozzle 2600 has already adopted the receptacle geometry. It's already been harmonized with ISO. And we've noticed in the field that the pre-cooling window is really 30 seconds is realistic. When we did the laboratory, we were a little bit, we learned from field data. And that was the purpose of the guideline, was to put it out. And we learned that partner stations in Germany, for instance, that 30 seconds is more realistic. That's great feedback from the field. We're also looking under hot soak conditions. I know there was a tremendous study underway from NREL data from the demonstration projects to individual automakers to get us to where we are today with regards to hot soak condition understanding, a real cross-section of what's out there for all the fuel cell vehicles worldwide, or most of them. And we're relaxing the hot soak conditions, which will give us what we think is a better fueling time. Dispenser temperature is moved to the breakaway. The breakaway, initially we thought as modelers that the optimal position would be right between the nozzle and the receptacle, but you can't measure that in the field, so we missed that. So we're actually moving it back to a place where the dispenser can actually measure it and then judge how the fueling is. We're putting in new pre-cooling categories because when we put together the TIR, if your pre-cooler went a little bit out of bounds, it was deemed they're supposed to shut down, and that was really unreasonable. There's no reason for that, so we're going to have this fallback fueling, and I'll show you that in a minute. I'll show you an actual example of that in a minute. Thermal mass of coupling components was taken into account. We're seeing that the fueling that we anticipated needs to be a tiny bit slower because of the thermal mass that we're seeing of the newest components. And we're trying to offset what I just said about the slower fueling time by having a slightly different category to focus a little more also on the commercial mainstream sizes. So expanded ramp rate tolerance to allow for less storage requirement on the station side. And I'm going to hand it off in a minute to my colleague Steve Matheson about allowing for a non-standard. This is a development method that we're actually going to allow in the standard, because the team believes that the MC method has merit, but probably needs a little more data before we hit the standard button. So we are anticipating to have a webinar and probably a workshop, maybe even in California, to go over the new updates, which you see here in values. And let me just show you one example of what I meant about pre-cooling categories. This actually came from a suggestion from our Japanese colleagues, Jari. And if, for instance, you own a dispenser today that's an A dispenser, pre-cooling time, pre-cooling window, I should say, hasn't changed at all. The type B dispenser has changed slightly, about 4 degrees if you have one today. And this new category, we're actually changing from the A, B, C, D nomenclature to T40, T30, T20, T0. And, being a little bit more precise, we think that we have the methodology that will allow fueling, and if the pre-cooler were to go out of place, for instance, from minus 33 because of overcapacity, or for instance, that may also be a factor. Or, we're hoping that there will be a lot more vehicles percentages than there are today. We understand that there's a significant amount of efforts for commercialization. Automakers have made their plans, and there'll be a lot more fueling If that happens, there may be instances where you go outside the window if the pre-cooler is a little bit strained. And if it just slows down a tiny bit to go to like another category, that's something we're saying it's acceptable. Keep fueling. Why do you need to slow down? So with that said, we'll come back with questions later, but I'm going to hand it off to my colleague, Steve Matheson.
Thank you very much, Jesse, and thank you, Rob, also for the introduction, and thank you, DOE, for allowing me to talk about some work that we've been doing on a kind of a novel hydrogen fueling approach called the MC method. So, advance the slide, thank you. So what's unique about the MC method, or maybe I should first explain what the MC method is. The MC method is an engineering model that takes into account a hydrogen tank's unique thermal characteristics, and it allows you to characterize that tank and develop some parameters that characterize that tank. These parameters are then utilized in some equations that allow you to accurately calculate the end-of-fill gas temperature. And so this is a pretty simple model, but it seems over the course of a lot of testing, it seems to do a pretty good job of predicting the gas temperature. So we've taken this model and we've actually developed it into a hydrogen fueling protocol. And what's kind of unique about the MC method is that this is a protocol that runs, the model actually runs inside the dispenser on the PLC of the dispenser. And it adjusts the fill dynamically, so it's taking into account what's happening during the fill. It's measuring, similar to SAE J2601, you can see here there's a number of inputs, but in addition to the J2601 inputs, we also take into account the tank parameters, which is circled, and we're also monitoring the delivered gas pressure in addition to the gas temperature. And the station uses all of these parameters to then determine what the appropriate fueling speed or pressure ramp rate is, and also when to end the fill for the ending pressure. So this is all done dynamically in real time. I just wanted to briefly go over the theory of the MC method. I know there's a lot of math and equations shown on the screen here. I think if we concentrate on the bottom part of this slide, and that gives you the sort of the key points. Basically, the MC, as we call it, is a mathematical construct, and it simply quantifies the heat absorption capability of the tank. So the units of MC are kilojoules per degree Kelvin. So you can think of MC as a heat sink or a thermal mass that has infinite thermal conductivity. So MC, of course, is dependent on a lot of different conditions. So we've developed an equation that you see on the bottom right side. So MC is mainly a function of your fueling time, but it's also a function of the initial internal energy and also how much energy is being added. And then with the MC, we can calculate the final gas temperature as shown in the red circled equation. Go ahead. So from the MC method, we've developed two primary fueling protocols. The first fueling protocol we call the MC default fill, and this is analogous to the J2601 lookup tables that Jesse just explained. It's analogous in the sense that the MC parameters are based on the boundary condition tank. So for determining what the appropriate fueling speed is, we use a large type 4, the same exact tank that's used for the lookup tables. And for determining the end of fill conditions, we utilize the MC parameters from a small type 3 tank, again, the same tank as used for the lookup tables. So what this means is that all vehicles are fueled the same way. The advantages of this are that we really don't need any communications, and it fills all vehicles the same way. The disadvantages are that we're not taking full advantage of the MC method, and because the fill performance is generalized for all vehicles. The other fueling protocol we call the MCID fill, or identification fill, and this is a fueling protocol that is exactly the same as the default fill, except this time instead of using the MC parameters from the boundary tanks, we use the MC parameters that are based on the actual tank that's being fueled. So this takes full advantage of the MC method, and it can result in significantly faster fueling times. However, to employ this method, we do need to have a secure method of communicating the vehicle's identification to the station, and this is still something we are looking into as far as what are the actual requirements for doing that, but most likely it will require a SIL level compliant communications. SIL is safety integrity level. It's an ISO document that it basically says what the safety requirements are for refueling, or for the communications part of it. So anyway, just to wrap up, the MC default fill is a general fill, and the MCID fill is a targeted fill for the particular vehicle. And then just to wrap things up, the benefits of using the MC method are for the customer, the potential for faster fueling times, and also very high SOC. And also for the industry, there's a number of benefits in that we don't need to use the station types or the pre-cooling categories anymore, because the MC method adjusts automatically to whatever the station conditions are. So this gives the station design a lot more flexibility, and also it incentivizes the station designers to if they design a higher performance pre-cooler, for example, they can actually see the benefit, and they'll be reflected in faster fueling times. So that's basically what I have today. Thank you again for the opportunity, and I'll hand it off to Jesse to wrap things up.
Okay, thanks, Steve. We are just I just wanted to put this slide. We just want to recognize it's a lot of harmonization that has gone that has passed the last few years that we've been doing this over 10 or 12 years. And one thing that's really clear is that in the very near future, the start of small-scale production of fuel cell vehicles is going to happen. And in that effort to coordinate the infrastructure and vehicles, there's been efforts in Japan, in Europe, primarily in Germany, and in the United States, primarily in California, to have hydrogen infrastructure projects that will match up with those needs and demands for fueling infrastructure. So in order for that to happen, though it may not seem like a lot, it is a significant, we're talking about tens of thousands of vehicles or so, well, starting with the thousands of vehicles, of course. All these stations, the 68 in California, the 50 in Europe, and the 100 in Japan, all are going to be using the J2601 standard. We've been very, very lucky that the industry has listened to this data produce protocol, and we look forward to standardizing that in 2013 to help with the buildup of this infrastructure. So to sum things up, the currently published guideline TIR provides a baseline of 3 to 5 minute hydrogen fueling based on the fueling targets in this tables approach. We're using IRDA infrared data communications that increase the SOC up to 100%. As I mentioned a number of times, in 2013, the 2601 is going to be validated, and it's based on literally the state-of-the-art math models and lab and field data. This is actually going to be tested in the field at a number of stations after the laboratory testing has been wrapped up very soon. The future standard will allow for development fueling. Steve just showed us this MC fueling method, which optimizes fueling based on the dynamic control and the tank properties. So that's it for us. I don't know if Rob, if you wanted to. take it over.
Okay. Very good. First of all, a big thank you for Jesse Snyder and BMW and Steve Matheson and Honda for the excellent presentation. We have quite a few questions coming in, and I'd like to say that please don't hesitate to submit questions, multiple questions, and even comments. We're interested in all the feedback from the participants here on this webinar. So at this point, we'll start going through the questions, and like I say, if we don't get to all of them, we will follow up at a later point. Maybe we'll start with one here that, and so Jesse and Steve, these questions, you can determine on some of these who's the best to answer. First question, how do you handle a vehicle that is fueled with 700 bar hydrogen and then pulls up to a 350 bar station, or vice versa?
Okay, if you don't mind, I'll address this. There's two things. One, there's a mechanical lockout of doing, basically of a 35 megapascal vehicle trying to go to a 70 megapascal vehicle. There's a, we thought about that. You could be downwards compatible, meaning a 70 megapascal vehicle can pull up to a 35 megapascal vehicle. One thing that's something that should have been on the list is something called this cross pressure fueling. If a 30 right now, there's something an investigation underway for the standard. If a 70 megapascal vehicle, which is allowed to fuel a 35 megapascal, decides to do fueling at a 35 dispenser megapascal and then go to 70, it won't be over temperature, but it will be a higher temperature than expected, and that's something that's going to be considered in the guide and in this future standard.
Okay, so we'll take another question here. This is relative to life cycle analysis for alternative fuel vehicles. They're looking at comparisons between electric vehicles, battery electric vehicles, and hydrogen. Do you, from an OEM perspective, have information on life cycle cost that's available?
Well, especially at SAE, because those are hats we're sort of wearing right now. We don't talk about so much cost, but I think that there is a question about durability of lithium-ion batteries. Nothing to do with automakers or brands, just the chemistry that they have a shelf life. It's a shelf life for 7 to 8 years or so, where they have to be upgraded. Fuel cells are targeted at 15-year, 150,000. And I think that those are, really the targets that are out there, and a lot of at least the technical papers and that I have seen, and the automakers that are working on it have really shown that they can do that. So that's really an advantage to the fuel cells, yes.
Okay, very good. Here's a question about the MC method. Is there already a SIL capable IRDA communication that has been developed?
So the short answer is no, but the current IRDA communications, as Jesse described, it's currently in J2799. It will be pulled into the next J2601. May already be capable of SIL compliance, but that's still to be determined. So there are some OEMs that are looking into that as to what the actual requirements are for SIL compliance with the current IRDA communications, so I don't know what those requirements are absolutely at this point, but we do think that it is possible to utilize the current IRDA with the SIL compliance.
Okay, very good. Another related question relative to the MC method. Is there any additional hardware required to use the MC method at a J2601 compliant station?
No. As far as hardware goes, there's no additional requirements. It uses the exact same hardware.
Okay, very good. There's someone asking about safety devices, and I know that this is a little bit off of the dispensing, but how is hydrogen safety sensors used to detect leaks on board vehicles from OEM perspective?
Well, let me take a step back, because I think that the real question is hydrogen fueling safe. So I'll answer it sort of from the station side and the vehicle side, if that's okay. The station side has multiple layers of redundant protection in what's called a pressure relief valve. So it's set at 10% above this non-working pressure, or 1.38. Whenever, if there's ever a fault or whatever it is, if there's ever any issues with the fueling, et cetera, usually the fueling stops it under all circumstances and software related at 125%, and hardware it opens it at 138. So there's no issues or concerns with overpressure and things like that. There are, on the vehicle side, in regards to safety sensors, I think I'm not really sure what this meant, but there are temperature sensors and pressure sensors during communications, fueling. You can hit the abrupt signal. And I can tell you from my experience on the safety on the vehicle side, that if there's ever to be sort of an accident where an airbag were to go off or anything like that, the high pressure valve is sealed, the high voltage electronics is turned off, and the vehicle is pretty much inert at that point. So I hope that answers the question.
Yes, Jesse, that sounds very good. And like I say, keep bringing the questions in. We still have some time to, we have numerous questions showing up here on our screen. So let's see, as we're going down through here, there's a question, just a general question about pre-cooling and how this is accomplished, and from a station point of view.
Okay. I want to make sure that it's understood that we don't prescribe what methodology, how you pre-cool it. However, there is, for instance, the best way to store, for a large station, to store hydrogen is liquid hydrogen. It's not because of a preference or not. It's just if you want, instead of having a football-sized field of, hydrogen storage tanks, if you want to have 1,500 or 2,000 kilograms of hydrogen, liquid hydrogen is probably the best way of doing that on the station side. And if you have cooled hydrogen close to absolute zero, you have a lot of energy that you have to use to warm the hydrogen up. So using that energy that's just being, literally given away to the atmosphere for pre-cooling is something that pretty much everyone who delivers liquid hydrogen will be doing. So that's one way of doing it. In the laboratory, it's done with like liquid nitrogen, bath. It's basically, heat exchanger, things like that. But I can't say how everyone does it, also because there may be patents out there. We care about the pre-cooling temperature, not necessarily the technology. As long as it's reliable, it's not prescribed.
Okay, very good. Thank you. Here's another question for Honda. What is your current position on 500 bar refueling versus 700 bar?
Yeah, that's a fair question. We have done some investigation in the past on looking at what optimal hydrogen storage pressures, and basically the industry is all pretty much consensus on 700 bar at this point, and Honda has announced that our next generation fuel cell vehicle will have 700 bar storage. So that's our current direction.
I also think I'd just like to mention there was a number of SAE papers published. There was a formal request brought forth to the SAE committee, and effectively through the consensus process of SAE, it was deemed as not appropriate, at least for the fueling levels. There is a nozzle that's sort of out there that never really has not been applied, but in order to get the real range that we're talking about, pretty much the entire automotive industry has said present state of technology, 70 megapascal or 700 bar or 10,000 psi is the way to go.
Okay, very good. Here's a question that is relative to the SAE standard, and what regarding intellectual property, what is the possible for other intellectual properties that have been published relative to patents on the SAE document.
Okay. Well, I'm not a lawyer, but I know that SAE has always said to contact them or have, with regards to any patent. I can say that the tables themselves, the numbers of the pressure and the ramp rate are not patentable because they were first published in the public domain, so to speak. And a lot of the methodologies used for hydrogen fueling, like I mentioned, pre-cooling, communications, there's been reports that were published well before any patents or anything were published. So there is enough information out there regarding the public domain. If you have questions regarding patent on SAE documents, we can't really say anymore because it's not really our thing to say. Please contact SAE.
Okay, thanks. Is SAE taking an action to define requirements for hydrogen meters that may be used to control APRR ramp rates or change the end customer requirements?
That's a good question. Taking a step back, there are a number of weights and measures organizations around the world. And there's California Weights and Measures here in California. There's NIST. In the United States, there's the Eichamt in Germany, et cetera, et cetera. And one thing that we're finding is that the state of art for hydrogen is not yet there for what conventional liquid fuels are at, which is 1 or 2% accuracy. The accuracy for hydrogen today, probably the state of the art, is between 10 and 12%. And that's a big question that we've asked ourselves. Well, what happens if you would have a constant massive flow rate? Would it help improve the accuracy, et cetera, et cetera? It's not only the average pressure ramp rate, which is a factor. In the United States, there's a code or a law that is called NFPA 52, soon to be NFPA 2. And in that law, it prescribes thou shalt have leak checks every 2 or 3 times that basically stop the fueling for 30 seconds and then start again. That immediately abrupt changes, things like that, is much more, let's just say, affecting of end result than the ramp rate. So yes, we are aware that metering is something that needs to be investigated. I understand that that's being investigated by the U.S. Department of Energy, in Germany, et cetera, and I think in Japan as well. But we've asked that question, and the average pressure ramp rate has been deemed to be the standard way. The MC method is, as Steve mentioned, much more dynamic. But I really think that the technology is the key for the metering side. There has to be a supplier to come forth to help us with the accuracy. Although I believe, and right now, that for instance in Japan, the first 100 stations, there's already been a decree that the standard for metering is actually not going to be applying to those stations because of this known technical challenge that's out there.
Okay, thank you. So here we'll ask a question. Is the updated J2601 document going to be submitted to ANSI as an American national standard?
Yes.
Okay, and let's see, a lot of good questions coming in. Question regarding the permeation leaks and the ventilation. Is this diluted as any vents going from the vehicle?
Well, it's not the document we're talking about, but 2579 does give a safety spec. By the way, 2579 is just turning into a standard right now, and it's the same as the global technical regulation. There are very finite values for allowable permeation, and it is minute, not enough to sustain any flame. So, hydrogen is the smallest molecule on Earth, in the universe, and it permeates it does permeate, but the levels that are allowed to permeate will not sustain a flame, or they're very incredibly low levels. So to answer that question, I think what was being asked was that But if it's further clarification, feel free to ask another question.
Okay, thanks. The next question, due to the potential of unexpected overtemperature, would you discourage 700 bar and 350 bar or other lower pressures being dispensed at the same dispenser?
I think what you're trying to say, I mean, like I said, we're going to address this historical fueling issue that you're mentioning in the standard, and we will have a topic. I think that's what you're saying is if it's at the same dispenser, make sure it monitors that, or maybe have a different dispenser that's 10 feet beyond. We're not going to get into those kind of details, but we will have something in the standard, and I really can't say anything that's currently in process from the team. Besides, it will be addressed in the standard.
Okay, thanks. We'll see. Here's just a general question regarding the range and the understanding of 1 kilogram of hydrogen is approximately equivalent to 1 gallon of gasoline. And is the target mileage range 300 miles is the question.
Well, for consumer acceptance of conventional vehicles, 300 miles seems to be sort of the magic number, and that's really where this where the kilogram value came from, and approximately. But so there's already been automakers that you can double that range, and get 600 miles, depending on how much storage you have on board and what your efficiencies of your vehicle are, et cetera, et cetera. So 300 is really kind of deemed as a minimum.
Okay, thank you. So relative to the difference between a Type A and a Type B dispenser and the pre-cooling, what kinds of, from an OEM perspective, what kinds of advantages and possibly incentives are there for a station manufacturer to have a Type A?
Oh, well, it's actually easy to see. If you want to get more money, you can have faster refueling for the same amount of time. It's really that simple. So you could have 3 vehicles, or you could have 4 or 5 vehicles pull up in the same amount of time as 1 vehicle for the same, so 5 times. What we're seeing is 4 times more fuel dispensed versus a B dispenser. So you be the judge. I mean, that's really the we care about from the automotive perspective, which I'd like to portray at least. From the automotive perspective, is we want to make sure the customers buy these fuel cell vehicles. It is really the first opportunity to make a ZEV vehicle commercially acceptable. That's really what we're looking for. And the 3-minute fueling has been deemed to be key. If you're asking for the commercial aspect, just do the math.
Okay. Here's a question about the tank qualification procedure. So if there is a new tank which has not been previously considered within J2601, is there a process for testing or developing new tanks?
I'm glad that Na Win did the introduction. Na works also at the DOT, but right now the global technical regulation and the 2579, it's led by Glenn Shuffler, by the way, but those 2 documents are very well aligned on what the certification process will be for the storage. 2601 just says make sure that it's certified according to those documents. So, if another vehicle pulls up with some mystery tank and it's not out of spec, then you need to talk to the regulators about that.
Okay. A lot of good questions coming in. We're sorting down through these. Thanks, Jesse and Steve, for all the answers here. Here's another one for the MC method. If the MC method in its inclusion in J2601, is Honda planning to fill vehicles to the MC method, or is there backup plan for other non-communication fills?
Well, yes. I mean, we'd like to see the MC method, used as much as possible. But if it's in the next version of J2601, it'll be categorized as development fueling. So most likely the vehicle will have to specifically request that fueling protocol, and of course not all stations will necessarily be employing that. So of course our vehicles will obviously default to the J2601 when if the MC method's available, then we would like to use that method as much as possible, as I mentioned.
Okay, and another question relative to the home fueling that was mentioned relative to Honda being a proponent for home fueling. Is this, do you think we will be able to have fueling protocol for home fuelers for H70?
Sure. As Jesse mentioned, it's not really being addressed currently in the current version, the TIR, and even the next version of J2601 isn't really tackling that. But certainly is possible. The one advantage to home refueling is that the time constraints that we normally be concerned with, or retail-like fueling, don't apply. So a slower fill is something that a customer will be could be potentially okay with. So most likely, since you're trying to keep costs low for home refueling, you would not want to employ a pre-cooling system. So yes, you'd need to develop the appropriate fueling protocol for a 70 megapascal non-pre-cooled or 35 megapascal non-pre-cooled dispenser.
Okay, thank you. So here's a question, and this is one relative to delivery. Is there a pipeline grid for hydrogen fueling stations? And when can we look at that type of delivery structure?
Do you mind if we turn to the DOE to ask? You guys have projections and things like that. Perhaps, do you mind if I ask that to you guys a little? Or do you want me to make my view? Okay. I will say that I think there is a few examples of pipeline stations. There was one here in Torrance, I think.
Just down the street.
Yeah. So they exist. Well, okay. Let me just say, in the United States and Europe, hydrogen is used for the widest uses to refine gasoline, and in order to do that, there's an underground network which are not public for numerous reasons. There's a huge underground network in LA for hydrogen pipeline. There's a huge pipeline station underway since the 1920s in Germany. I think there's something like that in Japan, and it is potentially, there's a potential to do that. It's a much lower pressure hydrogen. It's a different quality of hydrogen. Anything is possible. Hydrogen has a lot of possibilities. I don't have a crystal ball on what the method is of the future. This is the fueling sort of protocol, but there is examples in the city that we're sitting in right now of a pipeline station. Yeah.
Okay, thanks. So this is just a general question versus customer and the vehicles, and so as the vehicle is fueled, the gauge on board, the pressure versus state of charge, is there a standard for how the customer will know if he has a 90% versus 100% state of charge?
It will be the same type of meter. You'll know if it's almost fill or fill, but that's not prescribed in the standards. That's up to each OEM. It could be a digital readout, it could be analog. It's not for us to say.
Here's a general question about fail-safe shutoffs to protect the tank system.
Okay, I think I mentioned it before that you have to have a fail-safe to protect the vehicle on the station side. In regards to if there were to be, for instance, a fire, there is fire protection on the vehicle, there's fire protection on the station. So overpressure per over temperature, and with J2601 and with the standards that are out there, CSA and the NFPA, etc., we're already covered regarding overpressure.
One more comment is that if the station is using the IRDA communications, or the vehicle is using the IRDA communications, there is an abort signal that can be sent from the vehicle.
Yeah.
So that's an additional fail-safe that the station can tell the station to stop for any reason.
Exactly.
Here's another question relative to HDTA test for both SAP fueling protocols. So I guess it looks like the question is, will this test for both fueling protocols, and will this also test for metrology is the second part to that?
Oh, that's a good question. But I think that, I don't want to say both fueling methods. Eventually, we're going to have a standard that will contain all fueling protocols. That's what we're really trying to do. But the device on the other side is going to be a tank, which you can use to validate that you're, within the parameters of 2601, and you could, theoretically take that the tank and use it for metrology. Absolutely. However, you probably want to do the validation of the equipment before it goes in, sort of in a laboratory environment, not necessarily just ambient temperature.
Okay, this is a question relative to the current stations that are in place and the added stations. What have we learned from the demonstration phase that can be used for the rollout for 2015?
Oh, good question. What have we learned? Well, I already reviewed, I think, some of the lessons learned for the 2601 side. I think that there has been a lot of, I think that there is a need for a sort of a lessons learned document and sort of a way of streamlining the stations, because right now, unfortunately, every station is sort of its own creation. There's no central way of sort of streamlining the process. It takes 2 to 3 to 3.5 years to make one of these stations. So I think one of the lessons learned would be some assistance regarding to sort of the permitting process. I know that there had been some efforts in the past from DOE. I think that like realistic setback distance and things like that. I'm not sure that lessons learned, I think, is something that needs to be put forth. One big thing is to make sure to coordinate, taking this from a 10,000-foot level, is to coordinate the demand, as in with the chicken and the egg. Make sure that the station is being put into a useful location. I know the California Fuel Cell Partnership has done a great job putting together a map of where the potential customers are and where to put the stations and things like that. And that was from the lessons learned of sort of the the field of dreams, build it and they will come, which is a philosophy that doesn't work. And I think that's something that's out there. But in terms of the fueling protocol, we sort of captured that in this 30-second window, and also we want to make sure that we validate the fueling protocol in actual stations before we do anything. And I should mention, one of the stations we're going to validate it on is actually right here in the middle, and we're going to be doing that before we actually publish 2601.
Okay, thank you, Jesse. I guess looking down through the questions, there's still some more left here, but we only have a few minutes left, and we wanted to make some closing comments. So, like I said before, please continue to submit your questions. You can submit them via email if you have questions that come up after you've gotten off the call here, questions that come to mind. We were very interested in the feedback that we're getting from all the participants here. And so with that, I guess I'd like to thank again Jesse Snyder from BMW and Steve Matheson from Honda for the very in-depth presentation on the subject of fueling protocols. And with that, I'd like to pass it over to, from our DOE Golden office here, to wrap up the webinar for today.
Thank you everyone for joining, and just to remind everybody, we did record today's webinar, so the recording along with slides will be posted to our website in about 10 days. I will also send out an email to everybody once those post. You all have my contact information, allison.amen@go.doe.gov. So feel free, if you have questions after the webinar, please submit them to me and I will distribute them to today's speakers and we will follow up with you. And thanks again, everyone, and we really appreciate it.